lecture on advanced quantum detection. We ended the previous session, the previous lecture, with direct entanglement estimation or quantification aided by neural networks. Maybe some example would be handy. So let's say we have 10-qubit system. 10-qubit system is described by, generic 10-qubit system is described by a density operator or density matrix, some representation with the number of independent real parameters around 1 million. 1 million real parameters needed for describing such system if we are interested in the full state description. Actually, it's at the same time, it's a minimum number of independent measurements we need for full quantum state tomography. So this is also a quorum. And let's say we are not interested in the whole state. We are interested only on entanglement and particularly some subset of quantum correlations. Let's say we are interested in quantum mutual information parameters, which is basically, in our case, adjacency matrix characterizing all pairwise correlations between these 10 qubits or subsystems. So actually, of course, there is nothing at the main diagonal, and it's a symmetric adjacency matrix, so we are interested only in like 45 independent parameter of mutual information, quantum mutual information, which is quite a reduction. Of course, I stress again, this is not a complete entanglement characterization in the system, but this is something we can start. It includes also long-range correlations, of course, only pairwise, and it can be easily sort of generalized to higher order correlations because we have quantum mutual information also for triples and for nodes and so on. So this is actually quite nice measure which can be generalized. We can start with something simple and get to more and more detailed information. Okay, now we have to sort of fix some particular measurement scheme. So it can be set of random measurements, it can be some subset of Pauli, local Pauli measurements. It can be POVM, it can be local, separable, which we prefer. Or also, we can use entangled or collective measurements. There is no, no limits in this application. Anyway, we, let's say, fixed some number of measurements. Let's 10,000 measurements, which is only 1% of the quorum. And okay, and now we can finally construct the learning workflow. So at the input, we have our probabilities. And we have 10,000 of them. So long vector, but not as long as the full information about the state. This is the input to our deep neural network, which spits out the entanglement quantification we want. So basically, in our case, quantum mutual information and 45 elements. So if the network is trained like ready, the application is really straightforward, easy, doesn't require almost no computational resources. We just have our 10,000 measurement data, that's all, putting inside and in feed-forward manner we will get 45 number, that's all. It's easy. The question, of course, how it's trained. So we can't use measurement data because we need lots of states for training, and this is beyond the range, especially for 10-qubit system. So we train on numerically generated data, as we already heard. So basically, we generate some random quantum states, generic states, so partially entangled, partially pure, and so on, with different ranks. And now, of course, with the numerical state generated, we can compute the input for the network, ideal probabilities, and also we can compute quantum mutual information from this theoretical density operator. And so now we have this quantity predicted by the network, and we have this quantity which is ideal, or ground truth, if you want. And of course, we can compute an error. I mean, it's a vector of 45 numbers, so we can make some distance between these two vectors. They're actually after, I mean, if the quantum mutual information is defined as was shown somewhere before, like this, all these numbers are below, between 0 and 1. So actually, it's positive, two positive vectors, and we can easily compute their distance. And this is actually our loss function, which is minimized during the training. Based on this minimization, the gradients are computed, and the weights of the neural network are adapted. That's all. Yeah, of course, there are some issues. We mentioned already the thing with the random state generation, which it's quite hard in higher dimensional systems, or for higher dimensional systems, and I am not now discussing the computational challenges. I am talking about fundamental stuff, the concentration issue, where basically at least the methods we know, the states tends to cover only part of the whole Hilbert space, and it's even worse, the Hilbert-Schmidt distances and consequently purities and consequently also quantum mutual information concentrates to very small range of values. Again, this was discussed last time, and this example is an example of concentration of the quantum mutual information when going from 2 qubits to 4 qubits. You can imagine how it looks when we have 10 qubit state. So it's basically nothing. There are, of course, solutions to this problem, but they are extremely ad hoc, like combining several various generation methods for generating random states and taking part of the training data from using this method and tweaking this method and basically trying to expand the area of parameters and actually in both spaces because of course we need the random coverage or at least not missing any part of the space in input space, so in the sort of quantum states or probabilities, and also at the output space of the network. If in any space we will have sort of gap in our training data, then the network can't learn the sort of features in these missing areas. So okay, this is one problem. The second problem is it's better or worse than some state-of-the-art method. First, I don't know about any sort of state-of-the-art method for direct entanglement estimation from an arbitrary set of measurements or measurement data. Like, of course, if I design properly some measurement really with, having in mind the problem of let's say, distinguishing between entangled and not entangled or between some classes of entangled states, then I can tailor my measurement somehow, which actually this number also of these measurements also increases exponentially, but with the dimension of the system. But having something measured, for example, for different purpose, or just randomly sampling because we can't do precise measurement or full measurement, for quantum state tomography. And now having this measurement, it's a natural question. What we can say about some features in our state based on this data? And this is the answer. So, but we don't know about sort of state-of-the-art method to compare with. Only what we have is taking this data, making full quantum state reconstruction, even, knowing that this set is not tomographically complete. And then from the reconstructed density matrix, we can compute the entanglement and compare, which is, of course, not efficient. And also, there is a small problem that for 10-qubit system and test state of, let's say, only thousands of quantum states, the maximum likelihood quantum state tomography would take a year, probably, or definitely many days. Okay. And finally, and this is my point, basically, to having this example and motivate the next step. everything this, I mean, the whole model trained, now it works for the particular set of measurements and nothing else. Like if we change one projector or projection measurement here, we can't use this model. So it's specific. These models, and this was the results I showed you here, for example, and here for 2 qubits and 3 qubits and so on, are device specific. It works only for one particular measurement device. And this is something which is not sufficient for us. What we want is a single model, single neural network, if you want, which can process an arbitrary measurement. I mean, to start with. Ideally, even it should process also the systems with 9 qubits or 12 qubits maybe. So not just the particle dimension. But let's focus now to device independency or device agnostic solution. It would be the solution where we can put arbitrary measurement results here. It of course means that it's not enough to put data, measurement data. We also need to feed in the description of these particular measurements. And this is very, very preliminary results. The blue curve is entanglement error reached by device agnostic neural network. So still only for 2 qubits, dimension is fixed. But there is the maximum input, maximum number of inputs which has sense for 2 qubit systems. So basically 36 these inputs. But if you do not measure some of them, you sort of blank them somehow. We originally used zeros, like basically if we are not measuring the particle input, we put 0. Now I am pretty sure that it's completely wrong approach because zero detection is also detection, it's also information we discussed actually last course. So, I mean, how the network can, during training, distinguish between 2 cases. This input was measured, but the probability of, or the relative frequency of occurring this output was 0, or this particle measurement projection was not even there, like was not measured at all. So we need something different for blanking these unused inputs, probably something negative. So we are now working on this because we can't have minus 0.5 or minus 1 like a proper detection output. So it can be a reasonable sign for the network that the input is somehow special and it's not used. Anyway, this is still so inefficient and crude solution because you need the number of inputs same as the quorum. you maybe not you you don't use all of them, but still you need a vector of for 10 qubits of 1 million numbers, and you use only 1% of them, and the rest, instead of probabilities, you put -1, for example, in there. Not good. So what we need is architecture which can input and output arbitrary dimensions, which can, of course, be even convolutional network. We tried actually this result with the first layer convolutional, but technical details. We can, of course, we can sort of be inspired by large language models, which typically have different size of inputs and outputs. So recurrent network and other more complex architectures. But what I would like to try is graph neural networks, because especially for these outputs, which are also changes in dimension when the number of qubit changes. Then, of course, if the structure of quantum mutual information is a adjacency matrix. Adjacency matrix is equivalent to some graph. So it's basically sort of intuitive. For example, these outputs interpret as or represent by a graph. The input, I don't know so far. So, okay, this was like filling some white spots from the previous lecture. Now we can continue. So our goal is to have generic or general single model which can cover more measurement devices. And the question is if it's not too bold to ask for something like this. Are neural networks, deep neural networks, even sort of able to this kind of generalization? And I mean, we are fighting sort of with the solution for quantum systems, for entanglement quantification, but we decided to try this device agnostic concept on something else, on some classical system where there is a long history of using neural networks, and this is definitely imaging. Especially because we also think about some applications in our field, so like resolution and counting and localization of single molecules or quantum dots. I mean, the problem selected was single emitter super resolution imaging. And actually, it has lots of applications in classical microscopy, basically all single molecule localization microscopy, and there's stochastic forms like storm, palm, and so on. They use this, or I mean, this is the basic idea behind these methods. So, what is the setting? We have some object consisting of point-like emitters. Let's say we are discussing just only intensity, no complex stuff like phase, coherence. I mean, they are incoherent single emitters, which quite matches with many applications in this imaging field. We have optical imaging device, microscope or telescope in our astronomy, which is not perfect. It has lots of parameters, and depending on these parameters, like numerical aperture and the sensitivity and noise of the camera in the instrument and so on, it sort of destroys the original object, and the produced image is under-resolved. It has some finite resolution, it has some noise, and so on. And of course, I mean, the standard solution in these applications is learn everything about this imaging device, especially how this single blob from a single point emitter looks like. We call it point spread function. We need to know how it's wide and what is the shape of this function, and so many parameters. We can feed everything in the training of neural network, and after the network is trained, if we feed in the under-resolved image, the network predicts the original object. Okay, this is the idea. This is the standard workflow. The thing is that if anything changes, like, for example, in microscopy, high numerical aperture objective with numerical aperture 1.4 or something like this has focusing distance, depth of field, few hundreds of nanometers. So basically, if the position of the sample slightly changes, the system is slightly defocused, or actually, I mean, there is some change of focusation. It means the point spread function changes. Actually, over the working field of view, you may expect that all optical parameters of the optical imaging device are the same over the field of view. No, definitely not. There are aberrations. The point spread function is different in corners and in the middle, and so on. Plus, of course, you use different microscope, for example, because it gives us some other, let's say, the one is bright field, the other one is dark field, or polarization-based microscope, or something like this. So you change the instrument, and you, of course, it means that you have to train this network from scratch again, and you need a full calibration of your optical device. So what about to have a single computational model, single deep neural network, which is able to process images, such under-resolved images, from an arbitrary optical device without retraining? Okay, probably what we need is lots of data to train such a device-agnostic model. And again, it's not so easy to get lots of data from this microscope, that microscope, this defocusation, and so on. So, of course, plus we can induce some experimental biases there. So we decided to train on synthetic data, on numerically generated data. Actually, we generated a massive data set where several parameters, many parameters, is changing. Of course, we changed the positions, random positions of these point-like emitters. We changed the concentration of these emitters, so the number. It can be 1, 2, 3 emitters within the field of view, but also 1,000. they are completely overlapping in the unresolved image. But anyway. And we can change, of course, the size and shape of the point spread function. We can change the signal-to-noise ratio. We can even add some aberrations. I mean, it's basically up to you because, of course, I mean, no model is completely independent, device independent. You are still covering some range of the parameters. But I mean, it's quite huge. By the way, funny thing, we trained only for 2 shapes of point spread functions, not sizes. Sizes were covered, but only 2 shapes. Airy pattern, which is typical for low numerical aperture objectives, and Gaussian shape, typical for high numerical. But I mean, in reality, you never get this or this. You get something in between or even something more obscure. So, and after training, the network will be applied in the same, or applied in the same way. So we have some data we put in, and we get prediction. That's the same. The training is the challenge. Actually, same as for entanglement learning. Here we have lots of data, and these data can't fit. All the training set can't fit to the memory of even computer, not mentioning the memory of GPU with 24 giga in our case. So we use the technique. It's quite known, but definitely I suggest to think about this method in your project. It's incremental learning. Basically, it's a sort of on-fly generation of data. We produce some batch of data. We train the network on this batch of data for, let's say, 10 epochs. Of course, there are some mini batches and so on, but I'm thinking about like 1 million of data points, for example. And then we forget this batch and generate the other batch. And we train another 10 epochs on the new batch. And we are going like this. It was proved, that it's obvious that it's not so efficient like having the complete data set and train on it simultaneously. But I mean, this is only a feasible way for us. So maybe when, okay, maybe this is the better to start with. This device agnostic modeling network can really produce very nice results. For example, there is one example of one image. This is the original. This is the original image. This is a camera. Sorry, the original object. This is a camera image. You can see that the concentration of emitters is so large that you can't resolve the individual emitters. Actually, if we use the state-of-the-art packages for localization of single emitters, for single molecule localization, microscopy, and so on, these methods or these packages are completely lost. Yeah? So this is too high concentration for localization. And this is the reconstruction. This is the output of the network. And you can see that, I mean, it's more or less same. Here is the state-of-the-art statistical method of Richardson or Richardson-Lucy algorithm for reconstructing under-resolved images. And this state-of-the-art method, it knows the parameters of the microscope. The neural network doesn't know the parameters, the particular parameters of the microscope in this case. And by the way, these are not numerically simulated data. This is the experiment. Now, maybe you are asking how it's possible we know the ground truth for experimental data. Actually, these are not real emitters like quantum dots or molecules. It was measured using optical simulator, using spatial light modulator. The mask was basically demagnified to a very small image below the resolution of our optical device for observation, and it means we can get under-resolved images, but we also know what we are sending in, so we know the actual object. And in this setting, again, there is a comparison of performance of damped model and the baseline of Richardson-Lucy algorithm. And of course, now we have lots of parameters. We can plot these curves or measure these curves based on, we can change whatever. Here we change the emitter concentration, which actually means the number of emitters in this 50 times 50 field of view we use. So it's 1 or 1.5 order of magnitude improvement, despite the fact that the network knows nothing about the particle imaging device. So this is very nice, I mean, as itself, I mean, for applications in imaging, but for us, it's definitely some hint how to proceed further, how to train the device agnostic models, and of course, we are interested in entanglement. So, in future, we think of combining this device agnostic, deep learning aided super resolution with detailed measuring of number of photons. We discussed this a lot in a previous lecture. And using this, we first probably can increase further the resolution, but the main point is use the result for room temperature sensing with such single organic molecules. And of course, the work, I mean, is a work of my whole team. So these are credits and fundings. And thank you for the attention in the first lecture, but we will immediately continue the second part, and this is the tutorial on how to make correctly quantum state reconstruction using maximum likelihood. So first, maybe a very quick introduction to what are the possible measurement schemes in quantum measurement. Because, I mean, I already mentioned that quantum state tomography is a particular protocol. What are other protocols? We have parameter estimation, which means there is lots of prior information about the physical system. We basically know how the physical system looks like. We have complete description of its system, and we know that somewhere in this system there is a parameter. Let's say single parameter. It can be generalized to more parameters, but let's say single parameter. It can be a phase in an interferometer. It can be a distance between two bright spots. But anyway, this is, and this parameter, we don't know the value. What we have some data at the output. It can be distribution of intensities or at single photon level, or I mean in quantum level, these can be individual counts, number of counts at the detection outputs. And having this data, the question is how precisely we can estimate the value of this unknown parameter. That's all. The second very well-known protocol of quantum measurement is quantum state discrimination. And if parameter estimation is sort of in language of machine learning something like regression, if this parameter is continuous, then quantum state discrimination is more like classification. So again, lots of prior information everywhere. We have everywhere some prior information. We know the states which can sort of come inside the protocol. Let's say we have two states. So we know that there is a state A and state B. We know their full description. We just don't know if in particular run of the experiment, if we have A or B. They are coming randomly, in principle with some prior information. And the task now, obviously, is not finding something about states, because we know them. The question is how to design the measurement device in an optimal way to distinguish these two states shot by shot, it's single shot scheme, with a minimum error. It's actually designing an optimal receiver in communications, in quantum communications, let's say, but also in classical communications. And finally, there is a quantum state estimation, or I prefer the name quantum state reconstruction to distinguish it from the estimation of a parameter. I mean, of course, there is a gray area between these protocols. In principle, you can say, okay, but here my quantum state, a noun quantum state, is parameterized by some parameters, real parameters. So why not to use parameter estimation, multi-parameter estimation and estimation, and then what is the difference between estimation and quantum state reconstruction? But let's keep this, I mean, for further discussion. Quantum state reconstruction was already introduced here, so we have measurement device, which is the only prior knowledge here. We know our measurement device, otherwise, I mean, we know nothing in this protocol. We don't know the input quantum states. It's a multi-shot protocol. We can repeat, or we have to repeat the measurement several times. So we have n times this quantum state, and we know the ideal probabilities. I mean, for given quantum states and given measurement apparatus, we know the ideal probabilities. However, these can't be measured directly, we already discussed, so we measure only some number of occurrences of each measurement output. And in principle, we can normalize them by the total number of occurrences, so or total number of state copies, so we have so-called relative frequencies. And I mean, when I showed you these two examples for parameter estimation, so something which is more known in quantum optics, like estimation of the phase, but the second example was really imaging case, sort of. So maybe same in analogy, same example in imaging sort of a field of full state reconstruction. Now I omitted the word quantum, but this is the question, how much this is quantum or not. Anyway, we have a noun object here. It can be whatever, but let's say even some distribution of bright spots. It can be partially coherent, so it can also interfere. And we have measurement device, which is our optical imaging device, and some detector like CCD camera or matrix of single photon detectors, doesn't matter. And again, at the detector, we have some detection data, occurrences of how many clicks we have in each pixel. We can compute this if we know the state and the description of the measurement device. I mean, it's completely same. It can actually be described by this quantum mechanics formalism. But anyway, so this is also full state reconstruction, and we usually call it image reconstruction or image super resolution. Okay, so we have measurement data. We have our theoretical model, ideal probabilities. This part, the theoretical probabilities, is linear function of our unknown state. And if we assume that these two are the same, which are not, we already discussed, but if we assume, we can direct inverse. If we have enough equations if this system, we can make the inverse. And we already discussed all the problems connected with this approach. I mean, of course, this is a very fast approach, so it's still maybe a very good idea to try this first, to see what you get, if there are some problems or not, and then afterwards apply much more complicated approaches. Anyway, you all know, of course, the better strategy, especially if, for example, the number of equations here in the system is small or larger even than the number of variables. And this is least square solution, least square inversion. We basically make a distance between probabilities and measured data, and this P is a function of parameters of the quantum state, so we can minimize this functional over these parameters, and we have an estimate of quantum state. It's not easy to, I mean, okay, it can be done, but there are two issues. First, if formulated as this, there are no physical constraints. So what we get here is actually some matrix, which it's not necessarily a legit quantum state. Anyway, it can be done, even this somehow. The other problem is that this least square problem sort of doesn't reflect the statistics of the quantum detection. Okay, it sounds cryptic, but from classical statistics and uncertainty propagation and so on, you maybe know that the sort of typical solution is use likelihood, and in some limits, the likelihood and maximum likelihood estimation sort of converges to least square method. And mainly these conditions or assumptions are infinitely many or very large number of detection events, plus maybe some other things like statistical independency and other stuff. So basically, even from this classical theory, we know that this is only limit, and maybe not, it's not maybe the correct way how to do this, especially for a smaller number of detections. So what we have else? We have statistical methods. I mean, in general, they are fine. They don't require the equality between probabilities and measured data. And probably the most known method or scale, sort of range of methods is Bayesian inference. I mean, this is beyond the scope of this lecture, but I mean, even with basic sort of formulation of Bayes theorem, we have some hypotheses which are sort of testing. We are testing them, and we have some event which occurred, and basically we can formulate the posterior probability, which is the conditional probability of having the hypothesis, or I mean, yeah, that the hypothesis HI is there, under condition that we measured, that we observed the event A. And this posterior probability is more or less a product of likelihood and prior probability. Likelihood is sort of, again, a conditional probability which is inverse, or it's basically a probability, conditional probability of occurring the event A under the condition that the hypothesis HI was there. And prior is just prior, before the measurement, prior probability of having these hypotheses. So now let's formally sort of put our unknown quantum states as a hypothesis, and this event A is our data, the particle realization of data vector or data set we have. And now, of course, if we rewrite this, we have Bayes theorem for estimation of quantum state. This is extremely crude, and I am actually sorry for simplifying the Bayesian inference so much. But I mean, this is mainly to introduce, actually, this whole slide is here only to introduce for you the concept of likelihood and where it's sort of, where is it in the Bayesian approach. I mean, there is lots of work of using Bayesian inference in quantum physics and for estimation of quantum states, and they are very good work. So I am a little bit sorry for this joke, but I mean, this is general discussion between fragmentalist and Bayesian mathematicians in theory of statistics. Basically, everything is sort of centered around the discussion of about this prior probability, because how we can choose the prior probability. And if you are interested, I have very nice example how basically same problem can give you, physical problem can give you very different results, even if in both cases you choose a flat prior, so uniform probability of the I mean here, because it's the same problem, but I use some parameterization here and different parameterization here. These are not linear, and of course, if I transform the uniform probability from this parameterization to different parameterization, it's not uniform there. So this is sort of the catch, but we can discuss later. Okay, so now finally, what are the starting point for maximum likelihood? we have some set of measurements, and we are asking how likely this set of measurement outputs can occur given the fact that we started with some particle quantum state. So we are basically discussing this, this conditional probability. And I mean, it's simple. We have theoretical probability distribution of the measurement outputs, and now we can have each run, we can have only one click somewhere, of course, based on the probabilities. So we are sampling. We are just sampling from the probability distribution of the ideal measurement outputs. And this is multinomial distribution. So if we repeat the measurement n times, this conditional probability is just the multinomial probability of having n I occurrences for given PI detection output. That's all. Now the rest are basically formal derivation or reasoning. So first we can omit everything what doesn't depend on quantum state, because we are going to optimize over the quantum states. We were search in the space of quantum states. We will be searching the maximum of this probability. So I mean, numerical prefactor doesn't matter. Okay, we call this likelihood. And we very often, because we don't want to work with products, much better for us is working with sums. So we take a logarithm of the likelihood. We call log likelihood function then. Again, if there is a maximum for particular quantum state, when we of this likelihood functional, when we take not decreasing function of logarithm, the position of the maximum doesn't change. So we can make these changes. Okay, and again we can remove everything what doesn't depend on quantum states, which is the total number of measurements, and we have very simple log likelihood function, which is just this thing, this guy. And if you remember so-called Kullback-Leibler divergence, the distance between two probability distributions, of course, this is not it. There are other terms, but the other term is just an entropy of the, in our case, of data. But for given data, for fixed given data, it doesn't depend on quantum state. So we actually, you can think of maximizing likelihood or log likelihood as a, okay, and there is of course the minus sign, as a minimizing the KL divergence or distance between the measured data and the true probabilities or ideal probabilities generated by the state you are looking for. Okay, so this is formal formulation of estimator. By the way, the first idea of using maximum likelihood, basically with such formulation for quantum state estimation is from Zdeněk Radil, quite old proposal now. And okay, we are not ready still for maximization because we need physical constraints. We need to keep our density matrix physically sound. So trace of density matrix is one. Actually, it's also stabilized, sort of. We will see later. Anyway, how to include constraints in global maximization problem using Lagrange multipliers. Again, there are other ways. this is one example how to do. So we have this constraint, we put the one on the other side, we have something which is 0, and then we multiply by Lagrange multiplier, and it's still 0, that's all. Second condition, positivity or positivity semi-definiteness of the quantum state. We can easily use such decomposition. I mean, Cholesky is the original term or name of the guy who worked with this. For Cholesky, in Cholesky decomposition, the matrix A is upper or lower triangular matrix. We don't need this there. We actually don't need the Cholesky decomposition. We can take an arbitrary matrix, and if I multiply arbitrary matrix with its Hermite conjugation, we get the positive Hermitian matrix. So the whole functional now looks like log likelihood with this raw parameterized using this product, and additionally we have our Lagrange multiplier condition for trace normalization. We are looking for the maximum, so let's make a first derivation of this, and let's try the extreme point, so finding first derivation equals to 0. I mean, it's a little bit complicated because the derivation has to be done in the space of the quantum states. I prefer to call it variation. It's more close to correct mathematical approach, but still it's a little bit, let's say that this is approach for physicists, not for mathematicians. Anyway, so let's make this variational step. This or this, we can actually make both, doesn't matter. Yeah, I mean, slightly more correct is this way, so let's proceed with this. With such variation step, we basically looking for variation of log likelihood functional, which is this, and it should equals 0 for any arbitrary variation in a matrix. And of course, if we take basically Taylor decomposition of this L, we can see that we are really looking for derivative or in sense of variation of this functional versus A, and this should equals 0. So this should equal 0. This is the actual computation. The variation is quite simple. We have just the compound function. We have logarithm of linear function. Oh, sorry, logarithm of some function of A. So first we have to make a variation of logarithm, and then the inner function. The variance of the logarithm or derivative of the logarithm is basically 1 over the argument, which is here, and here, and there is then variation of A. We of course using only terms with the first order, first power of the variation of A. Okay, we have something like this, trace of some operator times this variation of operator should equal 0 for any this. And I mean, it means that this operator has to be 0 operator, and we have this equation now. It works in the space of matrices A. We can multiply from right by the matrix A. we can get this, which is very close to the final extreme equation. Now the question, what is the size of the Lagrange multiplier? As usual, we basically make some operation to use the original constraints. So we apply trace. Tracing this gives you probabilities. Probabilities go out. We have sum of relative frequencies, so sum of data. They are normalized, so it's 1. So mu is 1. That's all. We have final, almost final, extreme equation for an estimate for the rho, which maximize the likelihood, log likelihood functional. So this holds only when rho is our solution. We usually term this object here as a kernel or operator R, let's say. If we, by the way, if we make the whole derivation and if we make variations over in a row, not in a matrix, we would basically reach to equation R equals identity matrix. And again, we can apply this operator equation on a quantum state rho because it anyway operates on a quantum state, and we would get the same result. But with the A variation, it's much more. It's more correct. Okay, how to solve such equation? I mean, it's they are operators, and the kernel R, in nonlinear way, it contains probabilities, and probabilities are again functions of quantum state. So it's nonlinear. It's nonlinear operator equation. It's horrible. But if this kernel is this, if this map R is how it's called contractive, I am referring to functional analysis, then we can apply this iteratively and find a fixed point of this map, of this mapping, which is exactly what is done here. So basically applying this operator and iteration of this operator to nth iteration of quantum state, we receive or we get next iteration for quantum states, and we can repeat this process indefinitely, or I mean to stop it somewhere. So the full workflow. Let's start with some initial iteration, which can be, for example, the identity matrix just normalized to be quantum states, fully decohered, no information there basically. And we will discuss it later, but of course you can ask if the result of the whole iterative process depends on the initial iteration. No, it doesn't, and I will explain why in a minute. So then you compute probabilities because you have state and measurement. You can construct then the kernel operator, and you can make the first iteration of quantum states by applying zero kernel and zero quantum state. Okay, there is a small catch. Let's look at this first iteration of the quantum state, and let's see if it's Hermitian operator. Not really. I mean, only it would be Hermitian only if these two operators would commute, which they don't definitely in general. So how to fix this? Very easily. We just need to make this iterative extreme equation symmetric. That's all. So, I mean, we can have the extreme equation like the theoretical one, which works only for the estimate. Yeah? So, this one, make an Hermite conjugation, we get this because all these are Hermitian, and we just put this row here, and we have fully symmetric extreme equation, which now doesn't have problem with this losing Hermitianity during the iteration process. So how it looks iterative solution now, very similarly, it's basically the same process. And yeah, sometimes you won't or don't care about normalization of your data. So instead of keeping all probabilities and relative frequencies normalized and even controlling, I mean, of this normalization during the numerical sort of computations, it's much more convenient to just add normalization in each step. Okay, and when to stop? When we know that the algorithm sort of finished, we can count some maximum number of iterations. This is definitely not the exactly good approach, physical approach, but definitely it's fine to have this condition. I mean, as a safe check. And of course, we need to evaluate the distance between the subsequent iterations. And if it's smaller than something, then I don't know, numerical precision, we know that we can stop because the further iterative process can help us. By the way, very interesting thing. You all know the resolution of identity is a basic tool in quantum physics. Basically, if we solve any problem, if we change the basis, if we do basically anything, we can typically make a resolution of identity and put this resolution to this sum somewhere in our equation, and it helps. Yeah, and if you look at the extreme equation without quantum state, just the kernel equals identity matrix, it has a very similar form to identity resolution for this measurement operators, but these measurement operators are rescaled, and this is what maximum likelihood quantum state estimation actually does. It rescales, it makes weights to our measurement outputs based on their importance for the reconstruction of the given state. But okay, this is a little bit meta. So last note probably, how we even know that the process converged to something reasonable. I mean, the log likelihood functional is convex function of quantum states. And the space of quantum states is convex space. So we are looking for a maximum of a convex function over the convex set, and it means there is only one maximum, and this maximum is a global maximum, which is great because otherwise we will be completely lost. So we know that if the algorithm converges, then it converges to the correct global maximum because there are no other extreme there. So how to prove that it converges? Sorry, I can't give you the answer. At least I can give you the answer for the extreme equation and this iterative process we just introduced. I mean, there are other ways how to solve the extreme equation. There is, for example, this algorithm combining EM algorithm, expectation maximization, with optimal rotation of eigenbases or eigenvectors. But unfortunately, first, this algorithm is orders of magnitude more complicated for implementation, and is actually slower. Also, we can discuss the thing if we make the iteration, each step of this iteration, smaller, to not over jump the maximum. Yes, it is possible. You can prove that for sufficiently low epsilon, you can always increase the likelihood in each step of iterations, which basically means the proof. But again, you are making the convergence extremely slow. So finally, we don't have proof for the direct iterative solution of this extreme equation, but we so far haven't met any problem, any particular data where it doesn't converge correctly. Okay, and implementation in Python is quite similar, but I can think we can demonstrate it on real data, on real physical system, 2-qubit entangled state. So we have source, some parametric down conversion source of pairs of entangled photons. We a 6 Pauli projection measurement here on first qubit, same on the other. We measure all the combinations, so we have 36 real numbers which are written here. These are results of actual measurement. Okay, we now define the states and the projectors which we are measuring. So we're measuring states, horizontal, vertical, diagonal, antidiagonal, right and left-handed circular polarization. We are measuring the projective measurement associated with these states, and all the combinations which are like this. So separable projections, H, HH, HV, HD, and so on to LL. Okay, this is the function which contains everything necessary for maximum likelihood reconstruction. There is initial iteration defined. Here we compute now. In the cycles, in the cycle, we compute the probabilities, we compute the kernel, we make the new iteration, which is rho multiplied from both sides by the kernel. Okay, this is a little bit old Python anyway, and these are only auxiliary functions like for evaluation results, so how to compute purity, fidelity, and measure of entanglement concurrence. So, and that's all. Let's evaluate projectors, make a reconstruction. After less than 400 iterative steps, we get this density matrix, which for 2 qubits, it's 4 times 4. We see that there are basically only these 4 elements populated. The rest is almost 0 or very small. So it's probably something like Bell state psi minus. So let's define this, this state. I mean, the ideal theoretical state. Let's compute the fidelity between the reconstructed state and the theoretical psi minus. Yeah, okay, it's quite nice. The concurrent, the entanglement, if in this state, obviously, is also very nice. That's all. This is your workflow. No problem to apply maximum likelihood reconstruction in your project. The rest of the slides, actually, and if you are interested, we can discuss this afternoon after lunch. The rest solve sort of the special cases. Like sometimes, for example, you don't have the complete measurement. But the derivation I showed you assumes that the sum of the projection measurement, yeah, like these P operators, is identity. And if it's not fulfilled this assumption, then the derivation is not completely correct. We have to change it a little bit. And our extreme equation and then the iterative equation looks something a little bit different, but it's only small change. Okay, and that's all from me. Thank you very much. Or we can keep questions after lunch. Yeah, I will be happy, of course, to share with you the notebook, so the all codes, no problem. Actually, I was about to ask if there is some, I don't know, repository or something I can put it or. You can send me the slide and everything. Okay, okay. Mm-hmm. Okay, thank you.